Hello everyone, we are Team Tensor. Over the past few months, we have been collaborating with Pacific Northwest National Laboratories to develop a high-level C++ interface over MPI RMA called RMAX. We are attempting to design and develop an intuitive and composable interface over MPI RMA that can provide features needed by parallel scientific applications without sacrificing performance. Over the remainder of the video, you'll hear from 5 speakers: myself, Adam, Marcel, Blake, Derek, and Nathan.
Hi everyone, my name is Derek and I'm part of the Tensor team. I'm going to briefly cover what MPI RMA is and what our project RMAX is and why anyone should care. So MPI stands for Message Passing Interface, and it's a widely portable, low-level programming model that is used in many scientific applications. The benefit to using MPI is that programmers can utilize one-sided communication to greatly improve efficiency. However, the drawback to MPI is that it has a steep learning curve and it can be inconvenient to use. So what is our project RMAX and why should anyone care? Well, as we mentioned before, RMAX is a high-level C++ interface over MPI RMA that aims to decouple communication and synchronization of processes. To accomplish this, RMAX takes advantage of one-sided communication that is non-blocking asynchronous, as opposed to two-sided communication that is both blocking and synchronous. In other words, one-sided communication allows for better efficiency as it defers data synchronization instead of requiring synchronization to happen immediately before the program is allowed to continue. This allows for better parallel processing because it can avoid potential stalls or deadlocks that may happen with two-sided communication, but it can be extremely unintuitive to implement.
Hello everyone, it's Adam, and I will be covering global view versus local view. RMAX introduces a convenient abstraction, a window, also known as providing a window into some multidimensional array of data. You can visualize this as a line, a rectangle, a cube, or whatever. Its real superpower, though, is that both high and low-level users can leverage its capabilities. A local view window works a lot like a basic C-style array or memory allocation of a memory block. One process owns and controls it. As such, data must be explicitly shared between processes. This allows for a very fine control, but as it is mostly a wrapper around the MPI interface, it remains opaque and has a steep learning curve. Global view windows provide a shared, unified global array, and any processes have full access to any part of the array. Under the hood, the window is distributed and managed as a process local memory, but RMAX's logic allows referencing any region of the global window, even one that spans multiple processes, as intuitive as a local window would be, allowing for large-scale data sharing and operations to be largely implicit. Both types of window views allow for intuitive math expressions, allowing users to add, subtract, multiply, and divide a given subarray of the window by some other subarray, element-wise, once again across process boundaries in the case of global view.
Hi, I'm Blake and I'll be discussing what we've added to RMAX. In its original development, RMAX had very little structure for many important administrative tasks. This led to two major problems. Firstly, there was a lack of useful tools for building and diagnosing the code base. Secondly, some of the features developed were not constructed using methods and patterns commonly regarded as best practice, and thus RMAX is hard to maintain. In this sprint, our main goal was to add this toolchain back in, utilizing GitHub Actions continuous integration to ensure all code is functionally sufficient before it is added to the production branch. In doing this, only code that is minimally buggy and always working will be deployed. Furthermore, this sprint we made it a focus to hone, refine, classify, and add continuous verification to the testing environment to ensure tests work the way intended in the repository, so that we are able to increase the ease of future development. In doing this, we have been able to identify some of the largest and most important features, as well as begin to diagnose the most problematic bugs within the code base.
Hi, my name is Marcel, and I am going to be walking us through our demo here today. This is one of the RMAX test cases. We chose one of the simpler ones so that we'd have time to kind of go and explain what's going on a little bit more with the multiprocessing. So to kind of walk you through the code first a little bit, we start by initializing a 10 by 10 window across, in our case, two processes. So two processes will be keeping track of their own separate 10 by 10 windows. We initialize them by filling them with ones, and then we take this array of 15 twos, which again, both processes have their own of. And here on line 30, we add those twos to a patch of the window in process one. So here we kind of select this 3, 4, 7, 6, kind of in the middle of that 10 by 10 window. And we choose to add, which is what the sum operator does, to that patch on window 1. Important to note here that this should only affect window 1. Window 0 should be unchanged after this process. And then it just prints it out again. So if we go ahead and print our output here, it should compile rather quickly. And we can see that in the initial stage, we have a window filled with 1s, 10 by 10. And in the second stage here, we have 2 windows where 1 remains unchanged and 1 has that patch of 5s, which is, of course, the result of adding 2 twice to those initial 1s. And while in this case, it's a rather simple operation, such as just summing the same data twice, this could be over many, many more processes and include many different kinds of operations, in theory, in a larger, more realistic use case.
There were a lot of things that went well with our first sprint. We successfully implemented the GitHub Actions CI pipeline for robust development. We've categorized all the test cases, which will allow us to focus on satisfying groups of test cases rather than individual test cases one at a time. We've also begun adding extra test cases to improve the existing test coverage, since the included tests don't cover all possibilities. To more accurately simulate a scientific testing environment, we all applied for and received access to the Kamiak High Performance Computing Club and deployed our code base to their HPC nodes for faster run times. We held weekly meetings with our sponsor in addition to regular meetings on our own to encourage productivity. Here's what we'd like to improve. We'd like to gain a better understanding of why some of the test cases are failing. For example, is it the environment or the RMAX code itself that is causing errors? We would also like to cover all boundary cases that aren't already covered by continuing to add new tests to the pipeline. As a group, we want to utilize the Kanban board more than we did last sprint, so that we can more easily track our progress in real time. Lastly, since much of the sprint was us familiarizing ourselves with MPI RMA and the existing repository, we want to have a more hands-on experience with the RMAX code itself during the second sprint. Now, here's what we plan to implement starting with the next sprint. As stated in the previous section, we plan to use the Kanban board more regularly to track our progress. In addition, we plan to continue our regular sponsor meetings to keep a steady development pace and find a regular meeting time outside of sponsor meetings to promote productivity among the group. We also plan to begin modifying the existing RMAX code to satisfy the failing test cases and smooth out any problems with the Kamiak HPC nodes. Allowing error detection and reporting within the RMAX code would allow for more ease of development and bug fixing. We plan to allow users and the library itself to create and/or respond to exceptions that may occur during execution. And finally, we plan to replace the currently existing handles class with a more robust system for storing and retrieving computations from asynchronous expressions.